Hey, howdy. So, this is probably not the game that you were expecting. Heck, for a while this wasn't the game that I was expecting. But a question kind of entered my mind, and combined with the computer science classes that I've been taking recently, I was determined to answer it to the best of my ability, and I think I've arrived at a pretty good answer. So, the question is, this is a game by the name of Super Fighters Deluxe. The original version of it was released back in, I want to say 2011, and the deluxe edition was released on Steam in 2018. That's not really that important, but it is good context. Multiplayer of the game has been kinda dead for a while now, but it does have a fully functional map editor. And I have made quite a few maps in this game. I don't remember the final count most recently. Hang on. One moment. There we go. Now it should actually record properly. It's a bit of an older game, so naturally it's a bit weird to record sometimes. Anyway, I have made a lot of maps in this game. And among them, this most recent one is probably the one I'm most proud of, frankly. It is a recreation of the Turing-complete cellular automata, Conway's Game of Life, and those are words that mean things I'll explain as we go along. But first, let me give a demonstration of what this even does. I have an input state hard-coded in. I was trying to make a way so that you could dynamically change the input state, but this was giving me enough grief as it was. So as it is now, 1, 2, 3, 4, 5. These 5 states are the first states that will be activated when I hit this button. So I load into the map. It takes a while to load because this game is not designed for stuff like this. I push this button, and it starts up. So, as you can see, it's evolving organically, but it's evolving in a very interesting way, because this is what's known as a glider in the language of the Game of Life. It has a period of 4, I believe, but every time it returns to its original state, it's already moved. So it kind of moves diagonally in a pattern like this. And it keeps going up. You can see that up there's no longer any weird timers. That's the top of the map, so it just turns into a square. And a square is completely stable. So, first I should explain what the hell is going on. So, the game of Cellular Automata is a lot simpler than it sounds. You have a big grid of squares. In fact, let me actually... Best way to show this might actually just be by doing it over here manually. So, you have a grid of squares, and every generation, those squares evolve based on a set of rules. So let me go ahead, make this white so that I can put black squares over it. And let's suppose that you had a grid that looked like this. Now, the rules of Conway's Game of Life are as follows. A cell is born if there are 3 cells adjacent to it. If the cell has 3 neighbors in either up, down, left, right, or any of the diagonals, then, empty or not, it generates a new cell. A cell survives if there are either 2 or 3 cells as neighbors. Otherwise, the cell dies. Now, thinking of this example right here, we have 3 cells in a spoke. The reason I say it's a spoke is because the next generation, well, these 2 only have 1 neighbor each, so they'll both die off. This has 2 neighbors, so it lives, and these 2 blank spots on the left and right both become filled cells. So each generation, it will basically spin around. I should be removing and replacing the windows, but I feel like it's appropriate here. Now, another example that I could do is something like this. Now, how do you predict that this is going to evolve? In the present state, all three of these, in this sort of arch shape, have two neighbors, so everything here will live onto the next generation. When the generational shift happens, it will generate two additional cells, one right here and one right here. Now, though, we have a problem, because these two now have four neighbors each, so they'll both die off. This is what is known in the business as an oscillator, and the spoke thing was also an oscillator. Now, I've been kind of getting off topic. I'm more explaining the semantics here. Because the plan from here is to take that mechanism and emulate it within Super Fighters Deluxe. The reason for this is it has been proven through a bunch of research papers and a bunch of research by a lot of very high-octane mathematicians that it is Turing complete. Now, for something to be Turing complete, it's kind of hard to explain. At a high level, something is Turing complete if it can simulate arbitrary inputs and outputs from a Turing machine, which is something that takes in inputs on a tape and outputs something based on whatever you fed into it. Well, that doesn't mean a whole lot here, but what Turing complete essentially means for our purposes is it's something that that has the computational power of a computer. It can do basically anything that a computer can do. Now, if you played games like Minecraft or Dwarf Fortress, or trying to think of some others here, Life, Minecraft, Dwarf Fortress, and Magic the Gathering have all been proven to be Turing complete. Some of those are a bit more believable than others. Minecraft makes quite a lot of sense, and Magic the Gathering makes no sense at all, but trust me when I say that it is Turing complete. I'll link a research paper in the description that is absolutely ridiculous, but proves that Magic the Gathering is not only Turing complete, but the process that they laid out can be done in a competitive setting, which is just amazing to me. Now, another property of these Turing complete mechanisms is that they can emulate any other Turing complete mechanism. I made a video ages and ages ago, back when I had a bad microphone, about me making Game of Life in Minecraft. And that alone would be enough to prove that Minecraft is Turing complete, because it can emulate another system that is. So let's apply that same process here. If I could find a way to emulate the Game of Life in this funny little fighting game, then this funny little fighting game is as powerful as a computer. Now, how is that for a mission statement, huh? But, I mean, there's a lot of problems with that. But, let me just write out a few of these problems for the hell of it. So, our problems are... Let's see, what all would we need to figure out? We would need logic for the cells. We would need the cells themselves. We would need the logic, we would need the cells, we would need a way to count up neighbors. That also says problem 2, pardon me. We would need logic, we would need cells, we would need a way to count up neighbors, and we would also need a way to iterate over time. So let me go ahead, pardon me taking my time a little bit here, I just want to make sure that I'm doing this right. Put a player spawn here, let's grab some glass, just because I'm lazy, and I don't want to make a real map for this. And let's set up one cell right here. So this will be our basis for the cell. And the first problem, I think let's swap these two. Let's deal with the cells first before we deal with the logic. So I feel like the best way to represent these cells is with a player. And there are CPUs that I could use here, and I think, let me go ahead and make this, or actually I'll borrow it from the finished product for the sake of consistency. There's nothing special about this player, this is just as jet black as I can make it. And then profile info. I'll grab the little modifier too. All that really dictates is the size, but it works. And then from here we get into the stuff that I actually need to make myself. So we have a way to create a cell. Now we need a way to remove a cell. And the way that I ended up doing it was with this little zone here. Anything that enters the zone gets destroyed. And then kind of a simple mechanism here. We want it to be spawned in all at once and then get deleted after a short amount of time. So let's make this 100, true, delete everything, and then pipe over here and delete the original deleter, because it can't delete itself. So now, set this to false. If I add in some buttons, we can see it in action. One button to spawn the guy, one button to delete him. Oops, did not mean to save there. We can spawn him in. We can spawn in as many guys as we want, and we hit the other button, and they get deleted, and there's nothing left behind besides the group marker. I should set it to custom so that it doesn't do that every single time. And we're never going to have to touch this again, so let me just go ahead and do this. Just to make everything smaller for the sake of convenience. Okay, that's the easy part. Now onto the hard part. We don't want just whenever let's just say we have some arbitrary latch timer up here. I'll go ahead and make that. And I'll put in some text calling it the latch. And let's have it run every 2 seconds. And not hook it up to anything yet, but this will be what determines how it works from step to step. Now, I will hook it up to this, because we know that every single tick, no matter what happens, all the cells will get removed before anything fancy happens. So with that, let me go ahead and hook this up to the latch, just so it doesn't buzz unless we want it to. And now we get to the problem of the counter. How in the hell... because there's no way to store numbers here. So how are we going to store how many neighbors there are? This is the core of problem number 3. And what I ended up doing was using an alternating trigger. And by the way, if this breaks when I'm done with it, I'm just going to look over at the finished product, because this took so long to actually work out. I'm not about to spend an hour and a half debugging something that is only here for the sake of example. So this is what I came up with. You have the system that alternates from the bottom to the top and works as a counter of sorts. So let me go ahead and grab this text. And I can count up the numbers. 1, 2, 3, up and up, all the way up to 8. And 8 is the maximum number of neighbors that we need to worry about. Now, in theory, I could actually make this as few as 4, but the trouble is that there is no way to make the alternator stop firing consistently. I mean, I could disable it after it's hit 4 and then re-enable it or something like that. I feel like this is more convenient. And it's also way easier to visualize it. So, from here, we have a couple of problems. Because let's just say that this is the thing that activates. And we have something. Let me just go ahead and hook it up like so. After this triggers, after a short delay, we want this to get disabled again so that it doesn't just keep happening over and over. And now, as far as these go, we only want this to happen if n equals 3. If there are 3 neighbors, we want it to happen. So for the time being, let's just do this. And then for, oops, that is not activate, that should be enabled. This enables it, this disables it. So now, if I hook this up to our alternator, and then we test the map, I click 1, 2, 3. Okay, something is not going right here. First off, this should not repeat. Okay. 1, 2, 3. Still nothing. Alright, what's the deal? This is not hooked up to the... There we go. Now this should... I keep accidentally saving. Pardon me. 1, 2, 3. Now this should work. Perfect. And then it gets deleted on the next instance, because I haven't pressed anything else. I could keep doing this over and over. Or not. Something seems to be causing problems. Ah, wait. I haven't implemented the reset function yet, no wonder. Hang on, let me put this up here again to prevent clutter. Now we have a different problem. There's no way that I could wire this to just, oh, if input A, then tick up 1, if input B, reset. I have to basically do that manually. The good news is that this is relatively simple, even though it's a bit weird to think about. What I basically have to do is, let me go ahead, let's see. Something like this. And then let's go ahead and pass that all the way down. 3, 4, 5, 6. Lots of mindlessly punching in numbers here now that I think about it. Oh, I forgot to wire these up. So all these timers will wire up to the alternator. So what this is going to do is I'll have all of these get called once everything is said and done with the current generation in order to reset the timer. I could also, like, there's some nonsense that I could do with groups that might also work, but the wiring wouldn't work out very well if I tried that. Anyway, one more thing I need to add here before I call it done for now is I need to add a little bit more of a delay. Oops, these are swapped. So what the problem is, if I have it run through every single value 1 to 8, then it's going to activate all the timers along the way, which is not going to be good. So what I want to do instead is have this system set up, and I'll have it run at 200 and 200. I have plenty of time to ensure that this bit works, because these timers only ever get called when I need them to reset the counter. So every other time I'm fine with them just activating whenever. Okay, and then in the disable, I can add in all of this stuff. I'll add in activate on startup just for the sake of it. Okay. And now I just need to add in here that also activates everything there. So now, that was a lot of work for one function, but now 1, 2, 3, and it works. And now I can do it again, 1, 2, 3. Not gonna ask. Like I said, I'm kind of doing this on a lark. Let me, at the risk of messing up the understanding here. Oh, that's the wrong one. That was a failed version of it. This is the one that I want. So this was my eventual final version. And there are some things here that are like for optimization's sake, but this is the exact system. Ah, that was my mistake. It was running, I needed to have a 0 there as well. Either way. I have this system over here which just shows the current time, or the current number of neighbors. So if I run this through, it loops all the way back around, and then I can do it for 2s, I can do it for 3s, and I can't do it for 4s. So the reason why I can do that is because of these 4 triggers over here. This is the meat of the logic. Let me actually go over to the unnamed and grab these guys. This is where the logic comes into play. These are basically logic gates. Branch number 1 is simply if n is 3. If n is 3, this enables. And the second one is if n is 2 and something was here last generation. This activates this enabler. This enabler is the first flag that needs to get set. This is the second flag that needs to get set. Then the latch will run through both of these enable triggers, and if either of them are able to set this off, then this enable can happen, which spawns another player. And this disables everything, this enables everything, and this disables all of this logic after the fact. So that's everything. So from this point, we work on modularizing it, which is where all of these come in. So for things like the timers, I just made one group marker that you could wire up so that it hits everything. The disabler, the enabler, the other disabler. That was all that needed to be done. So now we can return back to this with kind of a better understanding of what the heck is happening here. So for example, pardon the flashing, but that's just the way that the background keeps being selectable. In fact, let me go ahead, lock the background layer. That should stop that from happening. There we go. So now I could simulate any arbitrary input that I'm looking for. So for instance, let me go ahead 1, 2, 3 there, and then 1, 2, 3 down here. If I load it up, and it takes a while to load again. Boop. It's that exact same pattern as the oscillator that we were looking at earlier. And my one regret is that there's not enough space to do something like a Gosper glider gun or some like super complex mechanism, but I mean, let me end off the video by showing something a little bit funny. This is what happens when you try to select everything at once. Bad things happen. Bad things like this. Okay, so not only did that screw up the camera, the FPS is now 1. Hang on. Oh god, the FPS has hit 0. We have hit the critical point. Click outside and hopefully that works. Click a couple of times. There we go. I can't go much further than this, unfortunately. Maybe in the future I'll try, but I mean, the fact that it lags every time the timer goes off says a lot about how inefficient the system is. That being said, one of the main things that is assumed for Turing machines is infinite memory, infinite time. So this is not actually a problem. This still proves my point. As weird as it is, this still proves that this funny little map editor is Turing complete. Now, in the description, let's see what all I'm going to have to leave in the description. I'll have to leave the research paper for the Magic the Gathering thing, and I'll also leave a link to a demo video. There's no commentary, it's just the glider simulation in full. But that's all I got, and that's what I've been spending basically the past 3 weeks mulling over. And I'm happy that it actually kind of works. I was fully prepared for this to be completely impossible, but I mean, I'm here. I did it. It works, I guess. That's all I got for now, though. Thanks so much for watching.